Hello and welcome back. In this video we're talking about differentiability and how to figure out if a function is differentiable or not. We start with a very technical definition of differentiability for functions of two variables. Now this is a whole lot of stuff I'm not going to explain. I just want you to see that there is a technical definition that goes along with it. I'll briefly mention geometrically what's going on here. A function of two variables is differentiable at a point if it's well approximated by a plane. So remember, for a function of a single variable, differentiability really meant that it was locally linear. Same idea here for functions of two variables, but instead of looking like a line, it will look like a plane. So linearity in two dimensions. So that's really what this technical stuff is saying, is that you can fit some plane to the function that approximates the function at AB well. The wellness is defined here. Exactly what I mean by well. So if you have more questions about this, you can ask me in an email or during office hours or something like that. But essentially that's what it means. We can put a plane on it that approximates the function well at that point, as good as we want. So if this is technical and I'm not going too much into it, what's the point of this? Well, there's some theorems that come out of this. And we're going to use those theorems to test differentiability of functions. So the important theorems I'm mentioning here, how do we know if a function is differentiable at a point? Well, one, it has to have partial derivatives. We have to actually be able to find its partial derivative, fx and fy. That's not it. That's not all of it, right? You can have partials, but we also need those partials to be continuous. So if you find these partial derivatives with respect to x and y, and they're continuous at the point AB, then f is differentiable at AB. So just having the partials is not enough. Being able to differentiate with respect to x and y, that's not enough for the function to be differentiable. We also need those partials to be continuous. Then we can say the function's differentiable. And then a nice theorem, this is an analog of the same theorem from Calc 1 for functions of a single variable. If our function's differentiable, then it's also continuous at that point. So if we know it's differentiable, it has to be continuous. All right, so let's put this to use with a little example here. This is a function we looked at earlier in the chapter, I believe in 15.2, we looked at this function, and we showed that it was not continuous at 0, 0. Remember that the limit as xy went to the origin of f did not exist. So we went through that example already in a previous video, so I won't do it again here. But remember that this did not exist, which implied that f was not, is not continuous. F is not continuous at the origin. But it's continuous everywhere else. I don't know if you remember this one. This is the one that looked like we pinched a plane at the origin. So what that means then in terms of differentiability, since f is not continuous at the origin, I'll go back up to this theorem. Right, we have the theorem, if f is differentiable at a point, then it's continuous at the point. So the contrapositive of this, that is to say an equivalent statement here, is if f is not continuous at AB, then it's not differentiable at AB either. That's the contrapositive, which is equivalent to this statement. So the fact that we know that our function is not continuous at the origin means it's not differentiable at the origin either. So f is not differentiable at the origin. All right, I want to show you something Well, let's find partials. I want to show that f is differentiable everywhere else. It's continuous everywhere else. Just because it's continuous everywhere else doesn't mean it's differentiable. That implication only goes one way. So I want to show it is differentiable everywhere else. So to do that, I can compute the x partial and the y partial, and then show that they're continuous everywhere except for the origin. So fx partial with respect to x. This would be not at the origin. What do I want to say here? Well, let's just symbolically figure out partial with respect to x. So let's see. Partial with respect to x here. I could use quotient rule since I have x in the top and x is in the bottom. So let's do that. Derivative of the top with respect to x would be 3y. Derivative of the top times the bottom, x squared plus y squared, minus derivative of the bottom with respect to x, so that's 2x, times the top, 3xy, so that'll give me 6x squared y, all over the bottom squared. And I'm going to say if xy is not 0, 0, this'll work. Looks like I will have an x squared y there, so this will simplify a little bit. Let's maybe do that calculation and simplify it. So what will I have? 3 yx squared plus 3y cubed minus 6x squared y all over, oh, this should be bottom squared, right? X squared plus y squared squared. 3yx squared, x squared y, yx squared, those are the same thing. So I really have 3y cubed minus 3x squared y all over this x squared plus y squared. And again, this is if we're not at the origin. So everywhere except the origin, this works. We can do fy. Now I want you to notice something here. X and y, we have some symmetry between the variables x and y. So that means if I just switch my x's and y's in this partial with respect to x, that'll be the partial with respect to y. So we should get here 3x cubed minus 3y squared x over x squared plus y squared squared would be my partial with respect to y. Now these two guys, now that we have our partials, remember just because we can compute the partials doesn't mean the function's differentiable, but we can see that these don't exist when x and y are 0, so these would be not continuous at the origin. We could do a little bit more work to actually show that, right? Take a limit as xy goes to 0. We would need to find a couple lines that give us different variables or different values, but we can show these are not continuous at the origin, but they are continuous everywhere else. So continuous everywhere except 0, 0. So that means f is differentiable everywhere except the point 0, 0, except the origin. Okay, so that's the first part. And then the other part is a little curiosity here. I mentioned that the partials can exist without the function being differentiable. So I want to show you how that works out. I'm going to compute the partial. So here when we did these partial derivatives, we could only do this because we were assuming xy was not at the origin. Otherwise, we would have had a problem. But I can compute the partials at the origin by using the limit definition. So partial with respect to x at 0, 0, well, that would be the limit as h goes to 0 of f of 0 plus a little bit, my y value 0, minus f of 0, 0, all over h. And my fy at the origin would be limit, again, limit h goes to 0. Now I'd have f of 0, I do 0 plus h, minus f of 0, 0, all over h. So now I can evaluate these things according to my function. F of 0, 0 is 0. And then if one of my x or y coordinates is 0, then this top will be 0 and the whole function is 0. So that means each of these is 0. This would be the limit. H goes to 0 of 0 minus 0 over h. Same thing here. 0 minus 0 over h. So that gives me 0. That gives me 0. So that's my partial derivative with respect to x, partial derivative with respect to y. At the origin, they both exist and are 0. However, the function is not differentiable there, as we saw over here. Because f is not continuous at the origin, it's not differentiable at the origin, even though the partials exist there. So that's pretty weird, but that's just the nature of differentiability in this higher dimension. All right, that's it for this video, and that's it for the section. I'll see you next time.